Hi, my name is Justine Harkness, and in this video, we'll look at how to identify changes in potential energy. In order to have potential energy, we must have both a conservative force and a distance for that force to enact some sort of a change in motion. And to think about what this means, let's consider gravity, since gravity is a type of a conservative force. So here we have the surface of the Earth, and we'll have some sort of a skyscraper. Obviously, this is not drawn to scale. And we have a person standing on the top of that skyscraper. Now, often we'll define the surface of the Earth as 0 height, and then whatever height this skyscraper is, we can just call it h. Now, at the top of this skyscraper, this individual has some potential energy because there is a conservative force, the force due to gravity, that would be pointing downward, and there is a height in which that force can act. So we see potential energy whenever we are dealing with gravitational, electrostatic, magnetic, and elastic forces, since all of those are examples of conservative forces. To change the potential energy, we have a force applied over a distance. And let's come back to gravity to consider how that works. Here we have again the Earth. And remember, the force due to gravity is always pointing downward. So if I were to take an object and increase its height, here, the direction of motion is opposing the direction of the conservative force, so this would see an increase in the potential energy. However, if I had an object that was moving down, since its path of motion is the same direction as that force due to gravity, this would see a decrease in the potential energy. So let's take a look at some examples. Now, in our first one, we have a ball is lifted into the air. This is looking at gravity, which of course is a conservative force. So we have the Earth, and then we have our ball. Now let's think about our motion and our force. The gravitational force will always point downward, and here our motion is going up. Since our direction of motion is in the opposite direction as our force, this would give us an increase in potential energy. Now let's take a look at B. A stretched rubber band is released. So here's our rubber band. And let's think about the force. Rubber bands are very similar to springs. So this is essentially going to be a spring force. And spring forces always oppose the displacement. So if it's stretched out over to the right, there will be a force pointing to the left, and this would be our spring force. Now let's think about our motion. If it's released, this rubber band is going to snap backwards, hopefully not hitting anybody in the face. But our motion is in the same direction as our force, so this would give us a decrease in our potential energy. Now let's take a look at C. We have a chair that we're sliding across the room. So we're just going to put a chair as our box. And let's think about the forces that are acting on this box, because we have a lot of different forces. So we have the applied force in order to get this object moving. To overcome friction, we have to have some sort of applied force. There will also be a frictional force that will be in the opposite direction as that applied force. This is force of friction. We have the force due to gravity, and we'll have a normal force. Now remember that it has to be a conservative force, and of these forces, the only one that's conservative is this force due to gravity. Now this is moving across the room, so we can say our direction of motion is in the same direction as that applied force. Now when we look at our direction of motion and our conservative force, notice that they're neither going in the same direction nor are they going in the opposite direction. Here they are at 90 degrees. So here there would be no change in the potential energy of the chair. Now let's take a look at D. Here we have an electron moving away from a positive ion. So let's draw in our positive charge. We have our electron. And remember that if I have a positive and a negative charge, opposites always attract. So here our electrostatic force will be an attraction. And in this case, we are moving the electron away from our positive ion. So our direction of movement is in the opposite direction as that electrostatic force. So we would see an increase in the potential energy of that electron. In E, we have an acorn falling out of a tree. So this is another example of gravity. So let's draw our tree here. This is going to be a pretty horribly drawn tree, but we have our branch and we have our acorn. Now the gravitational force, again, will always be pointing down, so that's force due to gravity. And our acorn is falling out of the tree, so it is also pointing down in its motion path. So our force and our motion are in the same direction, so we would see a decrease in the potential energy of that acorn. Finally, let's take a look at some satellite and electron orbit. So here we have a satellite is orbiting the Earth at a constant height. So we got Earth, we got our satellite. Notice that the force will always be pointing inward, since gravitational forces are always attractive. But our motion is always perpendicular to that force. Because of that, there will be no change in potential energy since we have to have some sort of change in height. So no change for part F. Finally, let's take a look at G. An electron orbits the nucleus at a constant distance. Because of this constant distance, there is no change in the potential energy because there's also no change in the height. Notice that parts F and G both dealt with orbit. In orbit, you'll have some object moving in a circular path around another object. And the key here is that we'll be orbiting at a constant height or a constant distance. In all cases of orbit, there will be no change in the potential energy because the height or the distance remains constant. So now you should feel more comfortable identifying instances in which the potential energy is changing.